welcome back to this second session. It's pleasure to have Joseph Landsberg as our first speaker for this session. He's from Texas A&M, and he's going to talk about tensors and algebraic geometry.
Yeah, so thanks a lot for the invitation. Thanks to the organizers for putting this all together, and thank you for coming. I was suggested by one of the organizers that I kind of give an overview of some open problems and progress towards them regarding tensors related to algebraic geometry. And I was feeling very guilty because I was not going to talk about tensor decomposition. And then we had a beautiful talk this morning on it, so I don't have to feel guilty anymore, thanks to Bernard. So let's get going. But before we talk about tensors, let's just talk about linear algebra. So you start with a matrix, which we can think of in multiple different ways, as a linear map, as a bilinear map, linear map two different ways. So there's a lot of different ways we can view this object. And we'll say it has rank 1 if it's a column vector times a row vector, which I'll just write as a little, our map T or M is just A tensor B. Oh, by the way, please just interrupt if you have any questions at any time. I can't really see the chat reliably, but I'm very happy if you just, turn on your mic and ask your question. Okay, so the fundamental theorem of linear algebra, which by now we don't think of as a theorem because it seems so obvious to us, but I want you to really think of this as a fundamental theorem, that there's all these different notions that coincide called the rank of our matrix or linear map. Namely, it's the largest way we can, by changing coordinates, render our matrix to be ones along the diagonal and zeros elsewhere. It's also the row rank, but the second thing is that the orbit structure in this space is very boring, because if we just even take the orbit closure, we don't get anything else interesting for this T. And then we have the row rank, the column rank, and we always know that the row rank equals the column rank, but I want you to really think of this as a miracle. And then the definition that is sort of one that generalizes most of tensors is the smallest r that we can write T as a sum of rank 1 elements. And another way to say that, in contrast to the first line, is that T can be obtained by a change of coordinates from this identity matrix of size r, which is padded by zeros. And again, we can also take limits and we don't get anything interesting. So this is all maybe not so interesting, but I want you to think of this as all very special things, because we're going to go to tensors. So instead of bilinear maps, we now have trilinear maps. Or we could think of it as a bilinear map that's vector valued. Or we can just think of it as a linear map from a vector space to a space of matrices. And an important example of a tensor, I'm only going to talk about three-way tensors just because all the subtleties are already in that theory. And for three-way tensors, if our three vector spaces are all isomorphic to some algebra, then we have the structure tensor of that algebra that encodes the multiplication rule for the algebra. And in particular, our favorite algebra, the space of n by n matrices under matrix multiplication, I'm going to give that a special symbol, the matrix multiplication tensor, just because it's going to show up several times in this talk. And just as with a two-way tensor or three-way tensor is rank 1 if it's a row vector times a column vector times a vector sticking out of the blackboard. Questions? Okay. All right, let's just do the same thing before. We have this kind of ones along the main diagonal and zeros elsewhere. And then we have this definition. The largest are such that we can sort of change coordinates and zero things out and get one of these IRs is called the subrank. If we allow ourselves to take limits, we get a new name, border subrank. And the fact that we have a different definition here indicates that these two things can be different. So sort of naive degenerations of our tensor, this thing now has maybe more interesting things in the boundary than before. Now we have row rank, column rank, and rank sticking out of the blackboard. And as indicated by the notation, these three things also can be different. They're called multilinear ranks. And then, like I said, the word that gets generalized to rank by tradition is the smallest r, that T is a sum of rank 1 tensors. And this can be rephrased such that, like comparing this line where we recover this IR from T, here we're recovering T from an IR. And again, we can take limits, and that gets its own name too, order rank. So now I'm asserting that all these things can be different. Any questions? Okay, even though they can be different, oh, yeah, and then we have this closure again. So there's interesting things on the boundary of IR as well, its orbit. They can be different, but they do satisfy inequalities, the smallest to the largest, and all these inequalities can be strict in various situations. If we have a generic tensor, unlike for matrices where the maximum possible rank was the size of the smallest vector space, here the maximum possible border rank is roughly quadratic, like m squared over 3, and that it's pretty close to that. But already we get our first open question. We don't even know what the largest possible rank of a tensor can be, even in quite small vector spaces. And there's this 4-author paper that's not that old that has the state of the art, which is, I mean, it's a beautiful paper, but the state of the art is rather primitive. Now, let's say we have all vector spaces of the same size and all the multilinear ranks are m, maximal. We'll call the tensor concise. These are kind of the interesting tensors. Otherwise, we should be working in a smaller space. And if a tensor is concise, then its border rank has to be at least m by the inequality above. And we'll say it has minimal border rank if equality occurs. And an open problem in this standard book by Bergeiser, Clausen, and etc., is to classify concise tensors of minimal border rank. And that's actually a very difficult problem. Not much is known about it at all. So let me switch gears for a second and talk about classical algebraic geometry. So we have some subvariety of projective space. We can define its secant variety. So we have the secant, sigma 1 of x is just x, sigma 2 of x is the points on a secant line to x or on a tangent line, etc. And this has been studied for well over 100 years. There's vast literature on secant varieties of projective varieties. And I bring it up now because this problem of studying border rank is studying membership in one of these secant varieties for the Segre variety, which is just the variety of rank 1 tensors. Questions? No? Okay, so let's talk about some more open problems. Let's go back to this problem of tensors of minimal border rank. And instead of trying to classify them, which is hopeless, I think, we can at least try to characterize them. That is to say, find defining equations for the intersection of this secant variety with the set of concise tensors. So that's some algebraic variety. We can try and find equations for it. The state of the art is not so good. So let's be a little bit more ambitious even, and let's just find defining equations for the secant variety itself. And here the state of the art is the same by Friedland, and it's only 10 years old, size 4. All right, so, but since if we want to talk about algebraic geometry, maybe we should be more ambitious and not just have set theoretic equations, but generators of the ideal. And here the state of the art is even worse. Okay, so let me do a different problem coming from computer science. Computer science is very concerned with explicit objects. So if you grab a matrix, if you grab a tensor at random, it will have border rank m squared over 3. But they want you to write down a tensor that explicitly that has border rank, well, maximal ideally, but let's just say a sequence, because in computer science they always deal with sequences of tensors, such that the border rank grows at least faster than linear. Even m log m, they would be happy. And the state of the art here is ridiculously bad. It's 2.03 m, and that 2.03 instead of 1.99 was really a significant advance, believe it or not. Okay, and then a problem I've spent a lot of my time on the last few years, the complexity of matrix multiplication. So in 1968, Strawson discovered the usual way we multiply matrices, namely row column, and that uses roughly n cubed arithmetic operations, is not optimal. And that gave rise to the question is, what's optimal? And there was a tremendous amount of work on this the next 20 years that kept on getting better algorithms, at least in principle, for multiplying matrices. Most of these were not practical, but at least asymptotically they worked. And it led to this astounding conjecture that as the matrices get large, it becomes almost as easy to multiply them as it is to add them. If you add two n by n matrices, you need to do on the order of n squared arithmetic operations. And the claim is that you can almost get that good. It should really be n to the 2 plus epsilon asymptotically for multiplying them. So this is just pie in the sky, wild conjecture as far as I can tell. But the state of the art is remarkable. It's far less than you might imagine due to work of many, many people. And it's a little bit bigger than, it's a little bit less than 2.4 now, asymptotically. And even practically, it's something like 2.7 or 2.8. So this is really amazing. But this kind of upper bounds were not found with geometry, really. So I'd like to sort of shift gears to get you to geometry. The first step is that Strawson realized that this structure tensor of matrix multiplication, its rank, captures the complexity of multiplying matrices, so that the rank is a valid complexity measure, which is nice, but not as nice as we would like in algebraic geometry. We'd like dealing with Zariski closed sets, and thanks to Bini, we can, that its border rank also captures the complexity. So now we're back on, home turf of algebraic geometry, and we can hope to do something about this problem. Let me talk about another problem coming from quantum information theory, cost versus value. In a nutshell, you think of a tensor as some resource that you're going to use to convey information between Alice and Bob. So not only, I name my vector spaces A, B, and C, but the quantum people really think of them as people. And a tensor is a way of conveying information from Alice to Bob and Charlie. And the approximate cost of a tensor is its border rank, and its approximate value is approximately its border subrank. To describe the actual cost and value, you have to go to an asymptotic setting. So you take your tensor and you tensor it with itself to get some high tensor power in some very complicated space, but then you regroup to have a three-way tensor. So the quantum people would say that, Alice, Bob, and Charlie share n qubits or something, but let's not go there. And then they have this asymptotic notion of border rank and border subrank, and this is sort of the true measure. And this occurs in many other areas. And there's some beautiful work on this problem by these authors, Kristendal, Vrana, and Zuidam, that puts this in a very nice geometric context and relates it to other notions that have arisen in this area. Questions? Am I going too fast? No answer. Okay. All right, so let's talk a little bit about this value, because I was saying to you the cost is some very classical object in algebraic geometry, but the value is kind of a new concept. It is a question about orbit closures, but this particular type of problem, taking orbit closure of some tensor that someone who doesn't like you hands you, is maybe a strange thing. And so what people have done is they've yet made further definitions of invariants of tensors that can be used to approximate these notions. And one of the early ones was due to Terence Tao, called slice rank. A very recent one is called geometric rank. And this geometric rank is beautiful because it relates to both classical linear algebra and classical algebraic geometry, question that's come up in the previous talks in this workshop, namely, well, a slight variant on it. We want to get spaces of matrices of bounded rank, that is a linear subspace of dimension m of the m by m matrices that's contained in the set, say, determinant equals 0, or rank at most R matrices. And more generally, geometric rank is discussing non-transverse intersections of linear spaces with this secant variety of Segre variety. And this is just the rank at most R matrices. So we really are back in the classical world. But if you've seen some of the literature on this, this is also connected to study of vector bundles on projective space and many other sort of sophisticated topics in algebraic geometry. You probably know that even though this is an extremely classical subject, very little is understood about it. Okay, so let's talk a little bit about lower bounding border rank. So the first idea is quite natural. We have an algebraic variety and we want to test membership in it. So we should look for equations of this variety, and then the tensor that we have show that the tensor we have is not in the zero set, or isn't the zero set. So the good news is this invariant variety is invariant under the action of a large group. And therefore, it's ideal, the space of polynomials that vanish on this variety is a module for that group. And so you can do a systematic search just testing highest weight vectors inside the ideal of all polynomials. You decompose it as a G module. And then for each irreducible G module, you take a highest weight vector, you test it on your variety to see if the module is in the ideal or not. But as we'll see, only very small cases are feasible. So let me give a very simple example just for 2x2 matrix multiplication. Already for this case was open. And if you try to look for polynomials in the ideal, you find that, say, for the 6th secant variety, the ideal is empty already in degree 18. So contrast this with matrices, where the equations for matrices of rank at most r are just of degree r+1. Here, we know we need degree higher than 18 for border rank 6. That's a little scary, because we're talking about polynomials in 64 variables of degree 18. Thanks to John Hauenstein and Christian Eichenmeier, we can say something about them, but otherwise it would be hopeless. And indeed, they found a module in degree 19, and they tested it on this particular tensor and found that it does not in the 0 set. And since all the way back, Terracini could have told us that every tensor in this space has border rank at most 7, that solved or gave a new solution to a long-standing problem about the first non-trivial case for the matrix multiplication tensor. But as you can see, that these equations are of such high degree, the game is over for this brute force approach. Questions? Okay. So second idea, a very standard concept in algebraic geometry is to look for determinantal equations. So we have a G module, in this case, the space of tensors. We have a G variety, in our case, the space of rank 1 tensors. And we find equations for the secant variety of our G variety by finding an inclusion of our space into a space of matrices. And then if the rank of the points on the variety is low, then the rank of the points on the secant variety as a matrix rank is low. So this is a very nice idea, because although we may be mapping into a very large space, it's efficient to compute minors of matrices. Determinants can be computed efficiently thanks to Gaussian elimination. And using these techniques, there was some progress in general. This was the first general progress in over 30 years. And but now things start getting interesting. So everything I've said so far involved kind of classical algebraic geometry. Now this theorem has a bunch of people responsible. Half of them are computer scientists who've never heard of zero-dimensional schemes that are non-smoothable, but somehow they discovered them. And the thing about them is that there's bad news, because the Hilbert scheme, which we saw this morning in Bernard's talk, is not irreducible once you get past 7 points. And the consequence, and what's even worse, is that these local unsmoothable schemes their spans can fill up the ambient space very quickly, size 6m. So if we use determinantal methods, we can only detect zero-dimensional schemes, and zero-dimensional schemes fill the space, their spans fill the space linearly. And in fact, we suspect it's more like 2 or 3m for this game to be over. So in particular, we cannot use determinantal methods to prove border rank higher than 6m. So this is like really depressing news that was discovered a few years ago. So we got to find something else. Okay, so let's take another idea. If we have a border rank decomposition and the tensor we're interested in as a non-trivial stabilizer, then if we have one border decomposition, we get a whole orbit's worth, and in fact, a whole orbit closure's worth. And then we look for Borel fixed decompositions. And this is kind of leads us to searching, but because it's searching among a very small set, you can actually say something new. And as you notice, the improvement of this over before was just killing off most of the error term, but it still is progress. And this result, though, more importantly, opened the door, because you're not going to get much further with this, but this opened the door for a very exciting development a year or two ago by the Baczynski family. And this really uses scheme theory in a fundamental way. So if we have a border rank decomposition, we have a curve of tensors of rank R that limit to our tensor. And this tensor of rank R, we think of it as R distinct points. And we can take the ideal of those R distinct points. And so we get a curve of ideals limiting to some limit ideal. And this ideal is graded, Z3 graded. And again, we can insist by the same argument as before that the limiting ideal is Borel fixed if our tensor has symmetry. And we get a whole bunch of new conditions on what this ideal can be. So we're looking not just for points, but for an entire ideal now, and we have much more restrictions. And I point out there's a subtlety here that this limit of ideals is taken in the Heyman-Sternfels multigraded Hilbert scheme. In particular, the limiting ideal need not be saturated, which causes a lot of headaches. And I don't have time to discuss those headaches or even the progress because we're almost out of time. But this is an algorithm that will produce all candidates. And then once you have a candidate, you have to decide whether it's a real one or an imposter, which is a different thing. So I'm almost out of time, so I won't talk about particular progress. I just want to also show how the quote scheme shows up. Back to this minimal border rank thing. And let's just say I have, when we think of the linear map, I get a full rank matrix inside B tensor C. And I can use that by taking an inversion to think of my space of matrices as a space of endomorphisms. And if my tensor has rank R, that space of endomorphisms is simultaneously diagonalizable. And if it has border rank, it's a limit of simultaneously diagonalizable. In particular, if you have simultaneously diagonalizable matrices, they commute, and that property is preserved under taking limits. So we are back to a almost 75-year-old or maybe 100-year-old question in classical linear algebra: which abelian spaces of endomorphisms are in the closure of simultaneously diagonal endomorphisms? And just to be quick about this, the algebra generated by this space leads to a point in the quote scheme by this Atiyah-Drinfeld-Hitchin-Manin construction, which has been exploited recently by Yelyshev and Sivich. And now we're working on exploiting it to advance the knowledge of minimal border rank tensors. And I thank you for your attention.
Thanks very much, Joe. So we are open for questions. We have some time for multiple questions.
Oh, I thought I was supposed to end at 20 after.
Oh, sorry, I thought.
Yeah, go ahead.
No, it's 30, right? 30 after.
Oh, I was wondering why I was under
yeah,
such.
I didn't.
I felt like I timed this thing okay, and then
I think you've done it perfect. We planned with a 10-minute break so we can have some questions and then time to refresh for the next speaker. So.
Okay, great. Well,
perfect.
then
Thank
ask
you.
the question, please.
Can I ask a question? So about the so computing equations of the secant varieties, and what about the degree of the varieties? So
yeah, the degree is extremely large.
So it's controlled, it's known.
Yeah, already for rank 1, the degree is large for rank 1 tensors. And I don't think it's known explicitly in many cases. There's a recipe to determine it, as you know, but I don't think this recipe has been carried out in anything but the simplest possible cases.
Thank
One
you.
comment.
Yes. Good to see you.
Good to see you too. The reason I tuned in on this was just for the word tensor, because working on the borderline with mathematical physics, I was interested to see whether your tensor was going to be something or something with indices. Centipede tensor calculus, as someone once said. My mentor, Yuri Reinich, had some things to say about that, and I'm about to put them in the chat.
Okay. Yeah, so I've spent a lot of time with this diagrammatic calculus with tensors. It's very nice for doing certain kinds of computation. It's also nice for sort of studying things when you have additional group action beyond general linear groups. Then it becomes very nice and has a lot of relations to knot theory and other things. Work of Deline and Vogel is, and going back to Hermann Weyl, has some beautiful things with that.
So I did get it up in the chat, and I just, it goes back to 1923 when Reinich tried to get people to realize that a tensor was a thing in itself, and that indices, coordinates, etc., were not the place to start. I think he even said the last thing you want to do is write it in coordinates. Knowing his love of the English language, though his native was Russian, I think that was a deliberate double entendre.
Yeah, he actually, Clifford already got away from indices, and you can even find the diagrammatic notation in Clifford's notebooks. Actually, in this tensor book, I actually reproduced from the library at Cambridge, thanks to a friend of mine, Mike Eastwood, some pages from Clifford's notebooks where he has this diagrammatic calculus that's used very much by physicists.
Oh, thanks very much. I'll try and follow up on that.